Something extraordinary has just happened on the Sun, and scientists around the world are watching every new update. A powerful X-class solar flare erupted from an active sunspot region, blasting an enormous cloud of charged particles into space. Even more important, early observations suggested that at least part of the coronal mass ejection could be traveling toward Earth. Stay until the end, because what researchers noticed after the eruption may be even more significant than the flare itself. The eruption reached X 1.1 intensity, one of the strongest categories used by NOAA to classify solar flares. At nearly the same time, shortwave radio communications were disrupted across parts of Earth's sunlit side, as intense X-rays struck the upper atmosphere only minutes after leaving the Sun. Unlike the slower particle cloud, X-rays travel at the speed of light, meaning their effects begin almost immediately once the flare is directed toward Earth. But the flare was only the beginning. Scientists quickly turned their attention to the expanding cloud of plasma, known as a coronal mass ejection, or CME. These massive eruptions can contain billions of tons of electrically charged particles. If a CME is directed toward Earth, it usually takes anywhere from about 15 hours to several days to arrive, depending on its speed. During that journey, experts continuously analyze satellite images, magnetic field orientation, and solar wind measurements to estimate how strongly Earth's magnetic field could be disturbed. At first glance, this may sound like something that only astronomers care about. In reality, modern civilization depends heavily on technologies that are sensitive to space weather. Satellites orbiting Earth can experience increased radiation. High-frequency radio communication may become unreliable. GPS accuracy can temporarily decrease in some regions. Power grid operators also monitor these events carefully because strong geomagnetic disturbances can induce electrical currents in long transmission lines. Most events cause only minor disruptions, but every significant solar eruption is treated seriously until its full impact becomes clear. This is why agencies such as NOAA's Space Weather Prediction Center monitor the Sun around the clock. Multiple spacecraft continuously observe the solar surface from different angles, measuring ultraviolet light, magnetic fields, solar wind, and expanding plasma clouds. Their data allow forecasters to estimate whether Earth is directly in the path of a CME or whether the cloud will pass safely to one side. These forecasts are updated repeatedly as new observations become available because small changes near the Sun can significantly affect the final outcome. One of the biggest misconceptions is that every powerful solar flare automatically creates a dangerous geomagnetic storm on Earth. That simply is not true. The flare itself and the CME are related but separate phenomena. A powerful flare may occur without an Earth-directed CME, while a moderate flare can sometimes launch a plasma cloud that produces noticeable geomagnetic effects. Scientists therefore avoid making immediate conclusions until satellite observations confirm both the CME's direction and the orientation of its magnetic field. That magnetic orientation often determines whether Earth's own magnetic shield will strongly interact with the incoming solar wind or largely deflect it. Another reason this event attracted attention is the current phase of solar cycle 25. During periods of increased solar activity, sunspot regions become more numerous and magnetically complex. As magnetic fields twist, stretch, and reconnect, enormous amounts of stored energy can be released in only a few minutes. That is exactly why scientists have observed more frequent strong flares during the current solar cycle than during quieter years. As researchers continued examining the latest satellite images, they discovered something that immediately raised new questions. The flare was impressive. The radio blackout was expected. Even the CME itself was not the biggest surprise. What truly caught scientists' attention was the unusual magnetic structure developing around the active sunspot region. And that was the part they were most eager to understand. The unusual magnetic structure was exactly what scientists wanted to understand before making any confident prediction. While the flare itself had already ended, the active region remained highly complex. Twisted magnetic fields can continue storing enormous amounts of energy even after a major eruption. That means one powerful flare does not necessarily release all of the built-up stress. In some cases, additional eruptions can follow within hours or days if the magnetic configuration remains unstable. Researchers, therefore, continued monitoring the region almost continuously instead of assuming the event was over. History explains why experts take these situations so seriously. In March 1989, a powerful geomagnetic storm caused the collapse of Quebec's electrical grid in Canada, leaving millions of people without power for several hours. Satellites experienced anomalies, and radio communications were disrupted. Then, in October and November 2003, the famous Halloween solar storms produced multiple X-class flares that affected spacecraft, aviation routes, navigation systems, and power infrastructure around the world. These events demonstrated that space weather is not simply an astronomical curiosity. It can have real consequences for the technology modern society depends on every day. Fortunately, today's forecasting capabilities are far more advanced than they were decades ago. NASA spacecraft, ESA missions, and NOAA's Space Weather Prediction Center constantly observe the sun using multiple instruments. As a coronal mass ejection travels through space, scientists refine their models with fresh measurements of solar wind speed, plasma density, and magnetic orientation. Forecasts are updated repeatedly because even small changes during the CME's journey can significantly alter its eventual impact on Earth. For this particular event, forecasters indicated that part of the CME could interact with Earth's magnetic field strongly enough to produce a G2, or moderate, geomagnetic storm. A G2 storm is not considered an extreme event, but it is strong enough to increase aurora visibility at lower latitudes than usual. Operators of satellites, aviation systems, and power grids may also take precautionary measures while monitoring conditions. Importantly, a G2 watch does not mean widespread infrastructure failure is expected. It simply means conditions are favorable for moderate geomagnetic activity if the incoming magnetic field aligns efficiently with Earth's own field. One factor remained impossible to determine immediately after the eruption. Scientists needed to know the orientation of the CME's magnetic field. If that field points southward when it reaches Earth, it can connect more efficiently with Earth's magnetic field through a process called magnetic reconnection. That interaction allows more solar energy to enter Earth's magnetosphere, increasing the likelihood of stronger auroras and greater geomagnetic disturbances. If the orientation is less favorable, the effects may remain relatively minor, despite the CME's impressive appearance. That is why experienced space weather forecasters avoid dramatic predictions until spacecraft closer to Earth measure the incoming plasma directly. Events like this also remind us that the Sun is entering one of the most active periods of solar cycle 25. Strong flares, fast CMEs, and occasional geomagnetic storms are expected to remain more common than they were during the previous solar minimum. Most of these events pass with little impact, beyond beautiful auroras and brief communication disturbances. However, every major eruption provides scientists with another opportunity to improve forecasting models that help protect satellites, navigation systems, astronauts, and critical infrastructure around the globe. So, while headlines often describe these eruptions as cosmic explosions aimed at Earth, the scientific reality is more measured. Researchers are not predicting the end of the world. They are carefully observing, analyzing, and updating forecasts as new data arrives. The Sun remains one of the most fascinating and unpredictable objects in our solar system. Understanding its behavior helps us prepare for the rare moments when space weather reaches our planet. I'll continue following this story as scientists release new observations and updated forecasts. If you enjoy clear, evidence-based explanations of earthquakes, solar storms, volcanoes, and other natural hazards, be sure to subscribe and join me for the next update.